So, these reflexes, it becomes important because the reflexes are going to help us with the movement of respiration. There's a ventilation that's going to take place. So what is it that's going to be affecting some of these receptors? We're going to find that we have this thing called pressure, and we're going to see some resistance. We're going to talk about the airflow. Pressure. We're going to find some gas laws that are going to govern respiration. Boyle's, Charles, Dalton's, Henry's. Yeah. Y'all are about as excited as I am. Okay, so what does some of this tell us? Your textbook is going to get very detailed about these laws. It's going to get into showing you the math on these laws and all that sort of stuff. No, okay? I'm not going to ask you to do that, all right? Sorry, Rebecca, but you're going to have to at some point.
Oh, I know. Thank you.
Okay, so, you know, my goal is to kind of show what happens with these laws, okay? You were going into respiratory therapy, and I was teaching respiratory therapy. Yeah, get into detail, but I don't think I need to. So what does Boyle's law tell us? Pressure is inversely proportional to volume. So this tells me volume, okay, and at this point we're going to say the volume of air, okay? So if the volume of air increases, pressure will decrease, okay? So for example, if our lung volume increases, for example, breathing in, okay, this internal pressure that I've got will begin to fall. But then, if my lung volume decreases, breathing out, the internal pressure will rise. It's almost like a suction of some type, okay? Where if you've got the suction, think of it pulling in, volume increases, and you push it out, that volume is decreasing, okay? So that's what Boyle's law is telling us. Charles's law. Oh, and one thing to remember about the gas laws. The gas laws are kept at atmospheric pressure, sea level, okay? So we here at this point in Virginia, I don't think we're 100 feet above sea level. We're very close to sea level, okay? At sea level, the pressure of air is considered 1 atmosphere, all right? And anything above sea level, it affects the composition of the air around us. And if it affects the composition of the air around us, it's going to affect the composition of the air in us. Okay? So, the laws are based, for the most part, on 1 atmosphere of pressure and a constant temperature. All right? Now, there are some gas laws out there that take into effect, there's not an ideal temperature, okay? And it's not at 1 atmosphere. Trust me, I'm not going there. Let your chemistry professor go there. I can't do that, okay? Charles's law. The volume of the gas is directly proportional to the temperature. Now what this says, if temperature increases, all right, if our temperature increases, then we get more molecules of the gas moving, I guess I should say gases, and if that's the case, volume increases. Did you ever in elementary school have the experiment where you took like the bottle and put the balloon over top of it, and then you just kind of heated underneath the bottle and the balloon blew up? And then when you took it away from the heat, the balloon deflated? No? Oh, that's a pretty cool experiment. What happens is, when temperature goes up, molecules bounce back and forth much faster, okay? When temperatures are low, molecule movement slows down. So if we're thinking of this in terms of a gas, okay, it's like if you have the temperature increase, the molecules start bouncing, they're moving real quick, okay, and it makes stuff inflate. It's sort of like, do you ever have the tire light in your car come on in wintertime? Okay, that's because during the heated times, the air is, you got more pressure in your tires because the air is hotter, okay? But when the air cools down, the molecules are not moving as fast, and it makes that pressure sensor go off because it thinks you don't have enough pressure in your tires. That's why you should never inflate them, you know, too much. But hey, just say. Now, Dalton's law. Dalton's law tells me, and this one I was kind of like, wow, they really got invented in lab that day, didn't they? That if I have two or more gases, their partial pressures will be the sum of them added together for the total. I know. So let's say that I have oxygen, carbon dioxide, nitrogen, even though there's more. But let's go with these three, okay? They've got a total of 100. I could have one, say 33, one at 33, and maybe one at 36. No, somebody do the math for me. I can't do that math. 34. Okay? And just having the partial pressure of the oxygen, partial pressure of the CO2, and the partial pressure of the nitrogen, I totaled 100. So basically the sum of all of them together is the total pressure.
People get paid for coming up with these things.
Yeah.
Oh, man.
You'd be shocked at what people get paid to come up with. It amazes me. Now this one, Henry's law. Henry's law is going to come back to bite us, okay? Because note what it's based on. It's based upon the air-water interface. I am at, or I'm talking about, the area of my respiratory membrane. Okay? So, his law is stating that how easily a gas dissolves in water will determine basically its movement and its pressure. And I'll say once again, CO2 dissolves more readily in water than oxygen. So what we're going to find, this law will affect movement into the blood, movement into the alveolar sac, movement into the tissues. So this will have an all-around effect on the movement of the gases. So his law is kind of interesting. So what's going to happen? Well, we're going to respire. I didn't say expire, respire. All right? Respiration. We're going to have starting respiration. What is it that can actually increase respiration? What can stop inspiration? We have in the brain the medullary respiratory center. It's a reverberating circuit. It is continuously active. It never stops. So those receptors that we have, the chemoreceptors, the irritant receptors, the stretch receptors, all right, all the information, the center is going to receive that information. What we're going to see is when we receive information, that's going to stimulate the parts of the brain that are now concerned with voluntary respiratory movements. When we take everything, put it together, we're going to create action potentials that affect those respiratory muscles. Think about the muscles between the ribs and the diaphragm. So what we're going to find, these action potentials that are going to get started, they will travel to the diaphragm by way of what's called the phrenic nerve, all right? And it's going to cause the diaphragm to contract. So if I'm looking at inspiration, starting respiration, if I've gotten the action potential, then if I get a potential to my diaphragm, and it makes my diaphragm contract, which way is that going to go? Down or up? It's going to move downward. Think about that. Everybody take a deep breath in with me. Okay, feel the movement of the belly. Oh. Everybody with me? So, diaphragm contracted down. If the diaphragm moved downward, did my thoracic cavity, did it expand or recoil?
Expand.
I get some expansion of my thoracic cavity. So now my diaphragm's moved down, my thoracic cavity has increased in size, I have taken in this air, I've made some of these intercostal muscles act up, okay? And I have taken all of this and I have caused my thoracic cavity to expand. Now, in doing that, I have those membranes around the lung, that pleural cavity, that are connected to my thoracic cavity wall. So if that's expanding, I'm making my lungs expand. And if I'm making my lungs expand, I'm taking in the air, and my air is going to go to my alveolus. Am I correct or wrong? So, basically, what I've done is I've taken all of this and I've expanded it. And at that area of the alveolus, I've made the pressure low because I'm increasing my air intake. Now, to increase my inspiration, there would just be more neurons getting affected. And then, if I want to do that deep breath again, don't ask me to breathe in that far. I'm not used to breathing in that far. Probably wouldn't do very good with respiratory therapy, but just say it, okay? Now, I've decreased that pressure, but what's going to affect all of this expansion that has taken place? What is that reflex called? The Herring-Brewer reflex. It's going to make sure that I don't over-inflate my lungs. So I'm going to have these little chemoreceptors. I'm going to have these stretch receptors, okay? They're going to get their action potentials, but this time their action potential becomes what? Not stimulatory, but what?
Inhibitory.
They're going to become inhibitory. So all of this that I have breathed in, that thing's going to stop, those little signals are going to stop, and my diaphragm is gonna relax. I'm gonna have those intercostal muscles, the other ones come into play now, and I'm gonna now expire my air out. So now my lungs are gonna recoil, my thoracic cavity is gonna get smaller, which means I'm not gonna be pulling open those alveoli, I'm gonna be pushing them closed, well, squishing them up, okay? This time, what have I done to the pressure? Increased it. So what's going to happen is the atmospheric pressure that's around us and other pressures that will be in this thoracic cavity, as pressures build, they're going to force us to take air in, or they're going to force us to take air or push air out. And that's as far as I want us to go with the gas laws until we talk about the movement of the O2 and the CO2 across the cells. Pressures affected. If I have not enough air, I'm going to have something make me feel like I need to begin inspiration. Once I have enough and I've expanded as far as I can expand, it's going to inhibit and push it back out. And it'll affect the actual pressure at that alveolar sac. Yes, no, maybe. All right. Like I said, give me till about 1:15, 1:30. You guys work on lab stuff.